Good morning, good afternoon, good evening to everyone who has joined the webinar today. We welcome and thank you everyone for joining us on an interesting discussion about enhancing industrial off-highway vehicle connectivity to maximize efficiency in environments like agriculture, construction, and mining. I am Chintan Fafadia, the VP of Product Management at PCTEL for our IIoT devices, and I'm joined today by our colleague and partner, Heikki Keränen, who is the head of technology at SATEL on this webinar. Our agenda today would include a brief introduction about PCTEL and our offerings. Then we'll discuss the wireless connectivity drivers for off-highway vehicles and the use cases in the environments like agriculture, construction, and mining for off-highway vehicles. And then after that, Heikki will walk us through some real-life examples of how they have worked on this and optimized the connectivity. At the end, we'll be taking questions. So we'll have time for the questions to be taken at the end. Please make sure that you put in your questions in the chat window, and we will try and address as many questions at the end as we can. This webinar is been recorded and will be available for playback afterwards. So with that, let's jump into the discussion itself. PCTEL as a company has been around for more than 30 years now. We specialize in antennas, test and measurement devices, and IIoT devices. In this webinar, we'll focus on our antenna offerings and the IIoT offerings that help us improve connectivity in this ruggedized and highly harsh environments for off-highway vehicles. So when you think about PCTEL, you think about antennas. It is for all different applications, for utilities, for public safety, for agriculture, construction, mining, and then our IIoT devices. We have access points, radio modules, which are Wi-Fi based, and then we have a sensor communication platform which has cellular, LoRa, and Bluetooth connectivity for different applications. So when we talk about off-highway vehicles and the connectivity, what are the drivers for this? Whenever you're talking about harsh environments like agriculture, construction, mining, you need to have them connected throughout the time so that you can improve productivity and efficiency. So, and there are so many different equipments that are used in this environments, like whether they are in construction, could be bulldozers, excavators, compactors. You need to have them coordinate with each other. When in agriculture, you're talking about this off-highway vehicles like tractors, they need to coordinate because if the farms are too big, and we need to know where each equipment is so that you can improve efficiency and productivity. Sometimes you're working 24/7. You need to make sure these equipment are connected, sending the right data back. This also leads to improved sustainability because you can reduce downtime, you can improve uptime, and you can improve the energy usage for your vehicles as well. And at the end, last but not the least, it's all about safety. You need to make sure that your environment where everyone is working is safe, and all those vehicles are working safely with humans, and they see these are off-highway vehicles, so you need to make sure that they are least accidents and they are connected so that we can avoid those type of situations. The major use cases for all this connected off-highway vehicles in environments could range across a multitude of use cases. For example, if you are in a huge farm for 500,000 acres, then you are doing camera sharing for remote viewing of these vehicles as they move around the farm, or platooning so that they're following each other in the right manner when you're doing different applications like harvesting. We'll also talk a lot about autonomous vehicles in our presentation today, and Heikki will walk us through real use cases where SATEL has utilized PCTEL offerings combined with the SATEL's offerings to in environments for autonomous vehicles to improve efficiency and connectivity. So with that, I will hand it over to my colleague and partner Heikki for him to walk through the different real-life examples and use cases. And again, I will remind everyone that please, if you have any questions, put it in the chat window, and we'll try and answer them as we towards the end. So with that, Heikki, over to you.
Thank you, Chintan. And thank you for the opportunity of being part of this PCTEL SATEL combined webinar. I appreciate the opportunity, and I'm going to talk about today indeed about enabling secure connectivity for off-highway machinery. And I'm going to do this presentation via example of autonomous excavator. How did we organize the connectivity for autonomous excavator? Before I go to this topic, let me quickly introduce my employer, SATEL. So we are a Finnish-based company from Northern Europe, country of Finland, southwest part of Finland. SATEL was established 1986, and what we do, we design and manufacture wireless connectivity devices. On the right top corner, you can see examples of our product offering. So we create radio connectivity units that are designed to be installed on heavy equipment, heavy off-highway machinery, or other industrial environments. And also we can provide that connectivity in form of a radio module that is the size of half of a credit card, let's say. And in this form factor, they are easily integrated inside a dashboard of a car or in a site surveying equipment or so. Inside OEM equipment. Via our partnerships with OEMs, we operate globally. So we have numerous global direct customers, and also we are represented by a global network of value-added distributors. We have this representation in over 100 countries. So we are a global company, even though we are one building here in Finland, in Salo. Those devices that we manufacture, they operate traditionally on UHF, VHF frequencies. So we talk about sub-gigahertz frequencies. During the last couple of years, we have been enhancing our portfolio with Wi-Fi solutions, where PCTEL offering is supporting us very greatly, and also 4G, 5G offering. And the research that I'm going to present today is a really important tool for us to make our radio connectivity solutions match the actual needs from the field. In this presentation, I'm going to focus on autonomous operation. Other applications where our devices are utilized are site surveying, smart construction, smart agriculture. In these above applications, one of the most common use cases where you can find SATEL devices today is RTK, which stands for real-time kinematic, the precision positioning solution, which works so that on the side of the construction site or agricultural fields, there is a base station that is sharing the correction signal, correction information for GNSS to the fleet, and thus the fleet will be able to acquire precise position in accuracy of few centimeters. So other solutions where we are used is smart mining environment, smart cities, for example, traffic light controls, as well as World Rally Car is not a mass market for us, but it's a good example of a solution where all the parts of the solution need to be durable and reliable, robust. There's a lot of dust and moist and vibration and so forth. So the equipment that is used there needs to be really solid and robust. So that's SATEL. And then let me go to the topic of enabling connectivity for autonomous excavator. We are fortunate to cooperate with University of Oulu that owns this excavator, and the remote control system and this autonomous operation system itself is owned and designed by Oulu University. SATEL is providing the connectivity part for this solution. And since we have this opportunity, we have been doing and still continue to do the research on finding the requirements for throughput, requirements for latency, requirements for signal robustness, requirements for signal quality, and in relation to signal quality also antenna placement, antenna evaluation. All of these are part of our research work that we do. And we are doing this research with both 5G, 4G connectivity, so cellular connectivity, as well as Wi-Fi. And when we started this research, our goal was to find which one of these technologies, whether it is Wi-Fi that is best suited for the requirements of this application, or should there be low latency 5G connectivity. So we wanted to see which technology fits best for this purpose. The excavator is equipped with LiDARs, IP cameras. IP cameras are especially important to monitor the operation. Even though if the excavator is operating autonomously, it is important to provide a mechanism to monitor what is happening in the surroundings of the excavator and provide an accurate view on what are the tasks that the machine is currently doing. And it's both process monitoring as well as safety feature to have live video from the excavator. LiDAR is also available for both safety purposes and also, for example, to track with point clouds what is the progress of the operation currently. As I mentioned, the accurate precision positioning is one of the SATEL applications. So inside this excavator, there's also a SATEL UHF radio modem for RTK reception combined with the 3D machine control system. But in this exercise, we are not focusing on the RTK itself. We are focusing on all the other connectivity that this excavator is requiring. And this connectivity is mainly, as I mentioned, the camera stream from the vehicle upstream to the remote monitoring center. And then from the remote monitoring or control center, there are commands sent over CAN bus wirelessly to the excavator. So when there's a central computing unit doing the calculation for autonomous operation, it is sending autonomously these commands to increase thrust or change the boom angles or turn the cabin or so. And when you send a command over CAN bus to the excavator, there will be a lot of sensor feedback. So angle sensor, for example, thrust sensor, RPM information, and this kind of information sent upstream, uplink to the central calculation. And now this central calculation can be either autonomous operation, or there could be an operator running the excavator with joystick control. We always run it so that from the base station, whether it is 5G base station or 5G core network or Wi-Fi base station, there's always a fixed connection to our remote operations center. So there's only one wireless link, and that's the last mile access from the base station to the excavator. The wireless client inside the excavator is our mission critical connectivity unit test bed. This is a proof of concept product or research platform. It's not a final product that could be ordered from SATEL off the shelf. It is made entirely for this research purposes, and it is equipped with 5G standalone and non-standalone operation. So it has a 5G modem inside. It has also a Wi-Fi card, PCTEL 2x2 MIMO card, 2x2 802.11 AC. That means Wi-Fi 5 card inside, with high output power to provide long distances. And it is designed to operate in this hard environment of a construction site. Here we have the PCTEL card, which is inside the connectivity unit. So this is the technology that provides us access to the Wi-Fi network. It can also provide the access point feature. It can also operate as a mesh node. And why we selected PCTEL, one of the reasons why we selected PCTEL is the industrial temperature range. So it is really designed with the industrial use cases in mind. And because of the mini PCI connector, it is easily implemented inside our router. So from the R&D point of view, the design with this card was quite straightforward. And to be able to connect to Wi-Fi or 5G, we need to have an antenna on top of the excavator, on the roof of the excavator. And in the beginning, in a couple of first use cases I will be showing to you, we have this PCTEL Trooper antenna installed on the roof. And we installed also a ground plane to make antenna characteristics even better. So to provide maximum gain and best radiation patterns, we provided this metal sheet to provide a proper ground plane. And as you can see, this antenna supports both Wi-Fi and cellular. It says LTE here, but also these frequencies are for 5G as well. And you can see quite high gain, so 5 decibel gain, for example, here for Wi-Fi. For cellular, and over 3 decibel gain for Wi-Fi, so pretty capable antenna. And it is very simple for us, since we had so many different antenna ports in this device. It is simple to just connect one antenna module radom to this device, and so simply enable both cellular and Wi-Fi. Okay, we first did some testing with 5 gigahertz Wi-Fi. We first verified that what is the throughput requirement. So we were able to send the video early evening. So the machines are halted already. They are not operating anymore on the construction site. But during the daytime, all these excavators and construction machines are operating here on the construction site. So the signal had to go through of this busy construction site all the way back to the construction site where there's a forest. We actually drove the vehicle, the excavator, into the forest. So this kind of forest is actually quite hard environment for the radio signal. So we wanted to make it not so simple use case, not so simple test case for the connectivity, and we drove the vehicle to the forest. The base station has an antenna 4 meters high, and this is the cabin where inside the cabin we have the autonomous computing unit and the remote control here inside the cabin. And we were able to run the signal over 500 meters all the way through the construction site, all the way to the end of the forest. And even in the furthest points, we were able to get more than 6 megabits per second available throughput, which means that, you remember, video and control data together, they were roughly 3 megabits per second. So video and control was possible to the end of the site. And here we are inside the forest, and you can see how the cabin is empty, and excavator is operating just fine. There are no issues on the operation. For demonstration purposes, we are just moving snow, but anyway, everything works smoothly. Little bit of additional boom movement here, but it wasn't because of the connectivity issues. Little bit of boom shaking, but I guess that was not because of the connectivity. Okay, so we were successful with Wi-Fi remote operation of the excavator. Then we wanted to compare with 5G. And as I said, the antenna that we installed, the Trooper 2 antenna, is capable of doing both. So we are really still continue using this Trooper antenna, but this time we are in the different location. So we are actually in a 5G network of a university, Oulu University campus. And one of the targets for this test was to see if enabling encryption has any effect on the excavator operation. So if the added payload in both traffic and computing, if this added payload makes any difference on the smoothness of the operation or so. So we first tried without encryption, and let me play back the video. It is a simulated environment, simulated excavation. The 5G campus network did not allow us to do any actual excavation, but we sort of did some not shadow boxing, but shadow excavation. And everything worked just fine with no encryption. And while we did this operation, we recorded the signal levels, and we had a very good 5G signal level. This blue line here in the top is solid good 5G signal level. Or actually, if you look any of these parameters that are all give some information about how good the signal is, all of them are very static and solid and robust signals. So we were happy about this operation without encryption. Then we run the same research with encryption enabled and wanted to see if the encryption has any effect. And this is what happened. The boom went wild. Luckily enough, it did not hit the car here. I can replay that. So everything started just fine, but then suddenly the boom went wild. And actually one of these scan commands that were sent between the remote control center and the excavation, some of the CAN commands was failing. It was coming too late, and thus the excavator operation went wild. And there was also a safety person there with the red button, but he was sleeping and did not hit the button in time to have an emergency stop. But luckily enough, nothing serious happened. But of course, we wanted to analyze, why did this happen? What was the reason? Was actually this fact that encryption was enabled, did it have so much effect on the reliability of the signal? Again, we analyzed the signal strength and signal status. And when we analyzed the signal status, we could see that the network was actually switched from 5G to 4G. This was, in this university campus area, this was 5G non-standalone network. It means that user plane is 5G or LTE, 4G that is, or 5G or LTE, and then the control plane is always LTE control plane. And depending on the network load, depending on the network conditions, the network will tell the user equipment to either use 5G or 4G. And now in the middle of the operation, network decided to guide our UE to the 4G. And this is when the packet loss happened. We could actually see from the timestamps that when the boom went wild, exactly at this moment where we have the red dotted line, exactly at this moment the boom went wild, and exactly this moment network was guiding us to 4G. And during this handover from 5G to 4G, there was packet loss. And this packet loss created unintended operation or behavior in the excavator. So what we wanted to do next is, okay, let's use 5G standalone network. We wanted to do this in a dedicated network that was not a campus network or public network, dedicated network for this operation and standalone. So we went to Nokia testing site. You can see it's winter again. So this basically happened winter, summer, and next winter. So we did this, or even more time in between. So we did this in a span of seasons. And yes, so this is a dedicated site. You can see the 5G base station, quite a small base station, but also the size of the operation area is limited. We don't need to have that powerful base stations correctly aligned, pointing exactly to the place of operation. And again, we have a control place where we have the computing unit and remote control. This is in a tower here, which provides a nice view to the place of operation as well. And let's see, with this dedicated network, 5G standalone network, let's see how did everything go. Let me start the play. And troubleshooting things to find out the reason. We checked the signal levels and everything. Finally, the reason was found when we climbed up to the roof of the excavator. So, as I said, all of these tests happened during the span of time, and meanwhile, we were waiting for the next test run. Oulu University did all kind of different tests by their own and installed all kind of equipment on the roof. I don't want to blame them. I mean, it is a great cooperation with Oulu University, and they are really great experts. So no blaming, but it is just an important point to see that you have to consider the antenna placement on the roof. You just cannot install all kind of different equipment surrounding your antennas. You can see here that this metal box is basically shadowing the whole side of the trooper antenna. And so what we had to do is optimize the excavator roof and antenna placement. And here we have the optimized roof. So you can see that all the excess equipment is removed from the roof. There's still some rust from that box visible here, but the box is now removed and the trooper antenna is totally now free from the surroundings. Actually, we wanted to even more optimize the connectivity and make sure that there's always a good signal towards the base station. Since we only have a small base station, we have to ensure that there's always good signal to that direction. So we installed these PCTEL BMLPV 5000 omnidirectional antennas to each corner. And we even fine-tuned the positioning so that in one of the corners we rise the antenna on top of the LiDAR so that it is coming above the line of all the LiDARs and cameras here. And when we did this fine-tuning with this omnidirectional BMLPV 5000, everything worked just fine. On the right side, you can see the recording of how the autonomous operation works now. Or actually now, when this video was recorded, there was this person called Samuli doing the steering with the remote control. But this PC that you can see in front of Samuli, this PC could be configured to run autonomous mode, but this time it was a remote control operation. And everything worked very fluently, as you can see from the picture. What wasn't so fluent was the camera work that my colleague did when he was filming this. So sorry about the shaky hand of the cameraman. Okay. So with 5G standalone network with proper antenna setup, everything was working correctly. Then we wanted to improve the connectivity a little bit more. So now we started to think that how about if this 5G base station goes down? You can see that there was only one 5G base station on this site with 3 radio heads, one base station with 3 radio heads. Also, when we did Wi-Fi testing, there was only one base station. So the system is totally dependent on the base station availability. And how about if there is a power cut for the base station, whether it is 5G base station or Wi-Fi base station? Both of them were operating itself very well in terms of performance, but they both provide single point of failure. So now we decided to make a solution that combines 5G and Wi-Fi. We were able to do this test with another testing site with other excavator. This is excavator of our partner from the machine control industry, and on their testing site we had an opportunity to operate in the direct vicinity of a 5G base station. The 5G base station is on the roof of this black building, and we also installed PCTEL Wi-Fi industrial access point to the side of the construction site or testing site. And we equipped the excavator with the same SATEL user equipment with the PCTEL Wi-Fi card and PCTEL omnidirectional antennas, and we installed those so that they are above the equipment on the roof. You can see on the lower right corner that all the antennas are nicely visible and extended on the roof. So the signal quality, whether it is 5G or Wi-Fi, the signal quality should be good. We started the operation here close to the building, and we moved then, or the excavator moved then to the other end closer to the Wi-Fi base station. And we enabled our intelligent software that is combining the 5G and Wi-Fi on a software level in a active hot standby manner, so that both of the connectivities are active simultaneously, and the software intelligently selects which path to use. And this picture that you can see in the middle, this picture is streamed from the vehicle, so it's part of the machine control system streaming the view to the construction site from the vehicle to the remote control center. So if you see a glitch in this video that I'm going to play, then there was a glitch in the data transfer over the wireless media. And now that I start playing this, you can see here 2 lines or 2 sections. There's a Wi-Fi quality value and there's a cellular quality value. And currently the cellular quality value 275 is higher than Wi-Fi quality value, so the cellular connection is better. So we are using currently 5G. As long as it says RMNet here, we are using 5G for the connectivity. And when the excavator is moving to the other end of the site, it will automatically swap to Wi-Fi when the quality value for Wi-Fi gets higher. So let's see how does that work. It's a little bit fast forwarded. First, we operate close to 5G base station. We are still under 5G network and using 5G connection. But now the excavator starts moving closer to the Wi-Fi base station, and very soon it is swapping. Now it did swap to the wireless LAN, and basically the swap was seamless. The data connection was running constantly without any interruptions. And now the excavator is coming back from the end of the site with Wi-Fi connection. It is going closer to the 5G base station, a little bit ping-ponging back and forth between the cellular and Wi-Fi, but then again statically connected to 5G, and the operation just continued without any interruptions. And also, even though it did ping pong between the technologies, it did not create any glitch in the transmission. So we were able to show that we can smartly combine two different technologies to make the connectivity even more robust. So the findings from our research were that both 5G and Wi-Fi both can perform well enough for autonomous operation or remote control operation. It doesn't matter whether it was autonomous or remote operated. Both performed just fine. But the optimal solution combines them both and makes it even more reliable. And one thing I want to emphasize as a result from this study is that it is not enough that you have a well-performing technology. It is not enough that you have 5G, the latest technology, or 5G, 5 gigahertz Wi-Fi, latest technology. You need to have a proper antenna system, reliable equipment, reliable router, and reliable components inside the router. So the whole path needs to be considered: network, antenna system, vehicle router. If you think the system as a whole, you will be able to create reliable connectivity for autonomous machinery. So thank you for your attention and time. And from my behalf, it's now time for questions if you have any.
Perfect. Thank you, Heikki, and thank you for walking us through these examples. This really stresses the point that you summarized at the end, that it's not, you cannot look at each system in a silo. It's the complete network that you have to think about when you are trying to provide constant and reliable connectivity for this off-highway vehicles use cases in ruggedized environments. So thank you for walking us through. These are really good teachings from your experiments and as you go towards the final productization of your products and bring it to market. We do have a couple of questions, Heikki, and if you don't mind, I can ask them.
Sure.
Okay, so first question we have is, for both Wi-Fi scenarios in the presentation, you set up an access point. How about infrastructure independent solutions? For example, vehicle to vehicle.
Yeah, that's a great question. That was one of the reasons why we selected the PCTEL card. Namely, it has the support for 802.11s, which is a mesh protocol. So with 802.11s, you are able to run connectivity between the units without any infrastructure units, without an access point. So they are, let's say, on the same hierarchy level. And when you have multiple 802.11s devices in the network, they can even hop through each other and form this kind of a hopping mesh. So each vehicle is able to connect to every other vehicle through other nodes in the network, through other vehicles in the network. So indeed, we do support vehicle-to-vehicle operation, and it is important to do so to support, for example, platooning or synchronous driving. In a smart agriculture, we have, for example, harvester and then a tractor and a trailer following the harvester. So to make them drive synchronously and stream video from one to another during this offloading of the harvester. This is an important example of such scenario.
Perfect, thank you. Another question we have is, if placing of the Wi-Fi access point provides more flexibility in managing the coverage than 5G, why not only rely on Wi-Fi?
why not only rely on Wi-Fi?
Mm-hmm.
The thing is that in many cases, these devices, they are moving from a construction site to another. And we are not sure if the next construction site has Wi-Fi infrastructure set up. So cellular network is something that you very often have available without need of setting up the infrastructure. That is one point. And another point is that we could lose the power from the Wi-Fi base station, or there could be some kind of a routing issue, or maybe there's interference. Maybe the wireless media is so much under congestion that data throughput is not adequate over the wireless media. So all kind of these different things can happen for the Wi-Fi network. So it's good to have a backup.
Makes sense. And I think it also depends on the application, right? If I'm not wrong, like you said, construction, you might be able to find cellular. But if you're in an agriculture environment where you are in a far off place, then you might just rely on Wi-Fi. So it depends on the application that you have, and it could very well be that dependent, that what technology you end up using. So you can rely on both to go back and forth, or you can only have 5G or only have Wi-Fi in certain scenarios where the other is not available.
Correct. And it could even change from day-to-day basis, depending on which site the vehicle is today.
Right. So another question we have is, how does your technology work? Vehicle to vehicle and or vehicle to infrastructure? And using which frequencies?
Yes. So it is a configurable parameter. We can make it in both vehicle to vehicle, so with a mesh, or in infrastructure environment with access point. So both are supported. And we do have 2.4 Wi-Fi on board, as well as 5 gigahertz Wi-Fi. And for 5 gigahertz specifically, we start from 5180, so little less than 5,200 megahertz, and then all the way up to 5.850. I believe that was the highest frequency.
Right. Thank you, Heikki. And I think we have
PCTEL antenna from PCTEL is a good option, where we can also combine the UHF support with the sweep antenna. So just by adding the sweep, we can cover UHF frequencies as well. And CMTA antenna is a good example because it has these mil standard specifications, and again, wide temperature range supporting industrial applications. So indeed, we are recommending these PCTEL antennas with UHF support for those scenarios.
perfect. Thank you, Heikki, and I hope everyone in the audience also found this webinar to be educational as they are thinking about enhancing industrial off-highway vehicle connectivity and improving efficiency for that for different environments. And if one thought that Heikki and I would like to leave everyone behind is think about it as an entire network and think end to end. Everything matters, from your system, your routers to your antennas. Everything matters depending on the environment you are in. Please choose the right equipment so that you have the right connectivity and the networks. With that, one last reminder, this webinar will be available as a recording, and we will share it with the audience who have signed up as well. So once again, we thank everyone that attended the webinar. Thank you, Heikki, for taking time and walking us through all your real-life examples here. We really appreciate that. And I thank everyone for joining this. Have a good day and enjoy the rest of your week. Thank you.
Thank you. It was a pleasure. Thank you, everybody.
Thank you.